In week 7, we're going to be talking about buffers, and there are two main types of buffer problems that we need to discuss. So here's the first type of buffer problem you'll encounter, figuring out the pH of a buffer, just the buffer itself. So here's an example. Calculate the pH of a buffer composed of 0.75 nitrous acid and 0.5 molar potassium nitrite. And the Ka of nitrous acid is 4.5 times 10 to the negative fourth. So we're still using ice tables. That's not going to go away for a while. But the only difference between a pure acid versus a buffer is that there's already something in here, right? In our previous calculations, if you were just doing nitrous acid, this would be 0. But because this is a buffer is composed of an acid, a weak acid, and its conjugate base, right? So this has already got something in it. So this is from the problem, this is from the problem, this is 0. We're still assuming this is 0 initially, okay? That's the only difference between calculating just a regular old weak acid versus a buffer. You're just going to have this little bit to deal with. And it's going to go up by x. We're going to make the 5% approximation here as well, because this is a weak acid scenario. We're going to assume that x is so small that when we subtract it out, it's still about the same, and that x is so small that when we add it, it's still about the same. So now, this formula comes from the notes, okay? It's just an equation from our notes. That's where that came from. So we're just plugging in H3O plus is equal to Ka times the acid over the anion. So there's my Ka, there's my acid, there's my anion. So that's 6.8 times 10 to the negative fourth. That's H3O plus though. The problem asks what's the pH. So to convert H3O plus to a pH, I just take the negative log, and my pH is 3.17. So buffers are not any more difficult than regular old weak acids. They just require a little bit of extra paying attention because there's already an anion in the solution initially. And that's the only difference.